Right, we are live. Hello, everyone. Um, Today we have a very, very special guest. But before I introduce her, I would like to give a little bit of introduction for San Jose Astronomical Association. We are a very active club in San Jose. We have been around for many, many years. And given the pandemic situation, we are trying our best to adapt right now, and we have moved a lot of our events to be virtual. So this is one of those events that we have been doing for years now, which is our guest speaker series. We every month we have a, a board meeting around full moon week on the full moon weekend, and we have a talk scheduled right after that. So but besides this, we also have like star parties and other events like solar viewing, which we are completely doing online now. So please feel free to check out our website, our meetup, as well as our YouTube channel that we have just recently started. And this is all work in progress. We are still figuring out the format and learning the ropes of it. So if you have any suggestions, feel free to contact us by going to sja.net, and all the board of directors and the program leaders have their email addresses on there. So we would love to have the feedback from you regarding that. Now, coming to today's talk, I have to admit I'm awestruck and I'm a bit nervous to introduce her, but it is my honor to introduce Dr. Jill Tarter, who is an emeritus chair at SETI Research at the SETI Institute in Mountain View in California. And she serves as a member of Board of Trustees for that institution as well. Dr. Tarter received her Bachelor of Engineering Physics degree with distinction from Cornell University and her master's degree and PhD in astronomy from University of California, Berkeley. She has spent the majority of her professional career attempting to answer the old human question, are we alone, by searching for evidence of technological civilizations beyond Earth. I mean, it's a question that has been on all our minds for as long as we have existed as a human species. And I think I'm really looking forward to hearing more from her. And if you have ever watched the movie Contact, you already are familiar with her, because her work has been portrayed by Jodie Foster in the movie. Her biography, Making Contact, was written by Sarah Scholes and published in 2017. So feel free to check out the book. I know I will. But without further ado, I would like to hand it over to Dr. Tarter to start the talk. Thank you, Dr. Tarter.
Thank you. Thank you for the introduction. And hello to all of you out there. It seems really still weird to be staring at a screen and talking to a bunch of folks, but I hope that we'll make a good job of it tonight. So I work with a team. I'm a radio astronomer. We're trying to answer this very old question of, are we alone? And we're trying to do it by looking for signs that someone else has a technology out there that's modifying their environment in ways that we can detect over interstellar distances. So although we call it SETI, the search for extraterrestrial intelligence, what we're really searching for is evidence of technology. And before we start talking about how to look for them, I think we need to start by reconsidering what we mean by here and now. So like the rest of you, I am here working at home, locked down. And in my case, that home is in this house in the Berkeley Hills, in the East Bay, and close to San Francisco Bay. And of course, right now we're all suffering from the fires and the smoke and the problems that are ongoing in the peninsula and in the Napa and Sonoma. But we are here. And if we are at the altitude of low Earth orbiting satellites, we'd see ourselves as here on the west coast of the United States of America. And since 1968, when Bill Anders took this photo as he was coming around the limb of the moon, we've been able to see ourselves here as all part of one planet floating in the blackness of space. And this became an emblem for the environmental movement because it is so profound. This is who we are. We are all on this planet. And the Cassini spacecraft in the summer of 2013 turned around and looked at us and saw us here, right? There is actually a little white dot below the tip of that arrow. That's us. That's all of us. And we'd had this view from 1990 when the Voyager spacecraft on its way out of the solar system again turned around and caught this pale blue dot in a ray of sunlight and dust. That's us. And we're actually here. Our sun is one of a few 100 billion stars in a galaxy that we call the Milky Way. Now, until now, what I've shown you are actual images. This is not an image of the Milky Way because we can't get outside of it to turn around and take that image. But this is a galaxy that we think very much resembles what our spiral galaxy would look like. And we have just, for the first time, succeeded last spring in mapping the Milky Way galaxy from the inside out, looking at the emissions of carbon monoxide with radio telescopes. We've actually been able to see all of these individual spiral arms and make a very detailed map of the Milky Way galaxy. And you can see, I mean, we're out here in the boondocks. We're not even anywhere near the center. And of course, that Milky Way is one of hundreds of billions of galaxies in the observable universe. And so all these little dots are not stars, but galaxies containing hundreds of billions of stars. And then, of course, when you look at this image, this beautiful deep field image from Hubble, you notice that some of those dots are smaller and fainter, and that's because they're farther away. And as we look out into space, because of the tyranny of light speed, as we look farther, we're also looking further back in time. And indeed, we've come to realize that we humans are intimately connected with episodes far away and long ago, right? We're sitting in an evolving universe, which we think is something like 13.8 billion years old. And we're now at the epoch of stars and galaxies. But we humans actually count our heritage. We trace our lineage very far back in time, and we are intimately connected with some of those events early in the history of the galaxy. So what do we mean by now? And how far do we trace our lineage? Well, we trace it back more than the centuries of our families, or the millennia of our architecture and our art and our various experiments with different modes of governing. We trace our lineage back over millions of years since humans branched off, excuse me, from the great apes. But we actually go farther back than that. We go back even beyond the 2.4 billion years during which the atmosphere of the Earth has been perfused with oxygen due to the labors of these blue-green cyanobacteria. And back before that, back beyond the 4.568 billion years since the formation of our galaxy, we go back to a large cloud of molecular gas and dust that was actually polluted with the end products of previous generations of stars, these beautiful remnants from supernova explosions, such as this modern one. And these distant explosions were incredibly important because the iron in the hemoglobin molecules in your blood, the calcium in your bones, everything heavier than helium that makes you who you are, that all came from a previous generation of stars that blew themselves up and seeded the gas cloud that would eventually collapse to the Milky Way. And so it's taken us roughly a millennia to piece together this story, to be able to understand that it really does take a cosmos to make a human being. And we're not done yet. There's still a great deal that we don't understand. And we are continuing on this journey, asking who we are, why we're here, what else is out there, and whether or not there may be something else that also studies the cosmos the way we do. So over my career as an astronomer, there have been two amazing game changers, right? And those are extremophiles, organisms that live in environments that we couldn't tolerate for even an instant, and exoplanets and perhaps exomoons. So the extremophiles have opened our eyes to a range of environmental conditions under which life can not just exist, but thrive. Life exists kilometers below our feet where there's no sunlight. Life flourishes in the equivalent of boiling battery acid. Life lives in the the waters of nuclear cooling reactors. Life lives at temperatures below the freezing point of water and up to 121 degrees Celsius above the boiling temperature of water. So we have been really had to change our thought about life and evolution. You know, somehow our minds are understanding this, but yet we still use phrases like the ascent of man, as if we're the pinnacle of evolution, as opposed to just one of the many, many, many branches in this tree of life that we have on this planet. And then we launched the Kepler spacecraft in 2009 and discovered that, in fact, there are more planets than stars in the Milky Way galaxy. And given the variety of life that we now appreciate by studying the extremophiles, there's a lot more potentially habitable real estate out there than we understood when I began as a student. And so we've moved from asking whether there's any real estate and is any of it habitable. We've now moved to ask the next question, which is any of it actually inhabited? And so astrobiologists are very eager to look at the atmospheres of distant planets orbiting other stars, to look and try and make a chemical assay of those atmospheres, to look for chemical disequilibrium, to look for atmospheres like the Earth and unlike any other planet in our solar system. The Earth's atmosphere contains both molecular oxygen and molecular methane. And those two gases are really reactive. You put them together and they will turn into water vapor and carbon dioxide. Yet our atmosphere has significant amounts of those two chemicals in disequilibrium. And the reason for it is because of biology on the surface of the planet, which keeps replenishing these gases as they combine in the atmosphere. And we've recently begun to wonder about the atmosphere of Venus. So there has been the report of the detection of phosphine gas in the cloud layers in Venus. And it's a bit controversial because it's a single line detection. And usually when we claim the detection of a molecular species, we have a number of different rotational and vibrational states that identify the fingerprints of this molecule. The phosphine, it's just one line, but I think it's probably going to, it's not a very crowded region of the spectrum, and this is probably going to hold up. But then the question is, where we find phosphine on Earth, we find that it has been biologically mediated, that biology is part of the process of making this phosphine. And so do we really know all the geochemical and all the different reaction networks, photochemical reaction networks that could produce phosphine? And have we been so exhaustive in our study of all of those networks that we can say that we can see no way of making that phosphine photochemically or geochemically, that it may require biology to do this, right? So no one's made the direct claim yet, but it is a tantalizing question. And it may turn out that the first life we detect beyond Earth is in the clouds of Venus. So that's life, that's biosignatures. But what we work on, the team that I work with, is looking for technosignatures. So our technology has made us visible over interstellar distances for many decades, almost a century. And we wonder if indeed someone else's technology might show them to us. And so that's what we've been looking for. And we started in the 1960s with radio telescopes. And then we moved at the beginning of the century to optical telescopes. And now at LIC, right, we're pushing down into the near infrared. And what we're looking for is evidence of signals that are obviously engineered. So here's what we call a waterfall plot. Frequency is plotted horizontally and time is vertically. And you see all the snow, that's noise, including a lot of noise from the galaxy. About 10% of that is from galactic radiation. But you can see two structures in there in frequency and time that are clearly not natural. And this is what the planet Mars looks like when we point a radio telescope at it, and the Mars Reconnaissance Orbiter and Mars Express are on our side of Mars, and we can capture their carrier waves that are helping to send back information to the Deep Space Network. So obviously engineered in this case. The other thing that we need to be mindful of is the now piece of the story. Because if technologies spring up in the galaxy or beyond, but don't persist very long, if they turn themselves off or do themselves in, unless they are very long-lived, we will not detect anyone, because there will never be anyone that's close enough in space so we have the sensitivity to detect them, and overlapping in time with our technology. Remember, the galactic timescale is 10 billion years. So if civilizations pop up and last 100 years, it's really not very likely that we will be coincident with them, coeval with them. And so we need to think about technologies lasting for a long time for success. But now turn that around. Suppose we do succeed. Then we know it's possible for us to have a long future. And so that's why Phil Morrison, one of the pioneers of SETI research, referred to SETI as the archaeology of the future. It's archaeology because the signals have traveled over long distances, and if there's information embedded, it'll be telling us about their past. But it's also telling us that we can have a long future. Now, Frank Drake did the first SETI search back in 1960, and most people say, well, you've been searching for decades and decades. You haven't found anything. It must mean that nothing's there. No, it just means that the parameter space that we need to search is vast. It's 9-dimensional. You think about spatial dimensions, temporal, frequency, polarization, modulation, 9 different dimensions. And if you make an estimate of what the volume of that 9-dimensional search space is, turns out that a good analogy is to say the volume of the search space is equal to the volume of all the Earth's oceans. And then ask how much of the oceans have we explored looking for these technosignatures? And the answer, when SETI turned 50, 10 years ago, the answer was 1 12-ounce glass out of the oceans. Now, 10 years on, we've built new equipment, it's going faster, and Penn State students did this calculation last year, and they said, nah, it's more like a little hot tub's worth of water, but still not a very large part of the ocean's vast volume, which is why that I'm not at all bothered by something called the Fermi paradox. So if you're not familiar with that, it goes like this. If there ever was, anywhere or any when, another technological civilization, then compared to the 10 billion year history of our galaxy, they would quickly have gone from the invention of technology to the ability to travel across interstellar distances. And then, no matter what your model, you'll discover that they will, they will populate the entire galaxy in a time that's short compared to the history of the galaxy. But we don't see them. They're not here. And therefore, they never could have been anywhere or any when. We have to be the first technological civilization. No, I don't think so. Not when you think about that hot tub's worth of ocean that we've searched. There's no paradox because we can't say they're not here. We can't say that we've even explored our own solar system well enough to have detected a technology. Oh my goodness. All right. We're going to get through this without coughing. All right. So
we can take a break if necessary.
No, I have some water here.
Okay, good. Thank you.
So one of the things that we have done at the SETI Institute in partnership with UC Berkeley is to build something we call the Allen Telescope Array. It's the first time that we've built a large radio telescope out of a lot of small dishes and a very large amount of computing to put the signals from all of those dishes together. So this is up near Mount Lassen. It has 42 antennas today. We had hoped to build 350, but we still haven't raised enough money to build 350. But we use the Allen Telescope Array daily to search for signals from someone else's technology. And there's, as of the last 5 years, there's another group that's also exploring, looking for technosignatures. And that's a group at Berkeley called Breakthrough Listen. It's funded by a pledge of $100 million over 10 years from Yuri Milner. And Breakthrough Listen isn't building telescopes. They're building signal processing backends and data recorders. And they're renting time on existing telescopes. such as this, and as they were at the time, what are they doing? They're looking at the 43 closest stars to us, and we're still actually adding to those numbers. We're still occasionally finding a new star within 5 parsecs, but just one that's so red and faint we hadn't found yet. They'll look at 1,000 stars across all spectral types within 50 parsecs. They'll do a much more cursory search for 1 million nearby stars in the plane of the Milky Way. And they'll look at the center regions of at least 100 galaxies and, of course, exotic objects. So just as we use the Allen Telescope Array to look at Oumuamua, an interstellar visitor, when it passed through our solar system, they also used their telescopes and will continue to look at any kind of exotic objects that turn up. So they are using the 100-meter Green Bank telescope in West Virginia at the National Radio Astronomy Observatory. They rent about 20% of the time on that telescope, and they bring these wonderful data recorders and signal processing backends. They're also renting about 20% of the time at the 64-meter telescope in Parkes, New South Wales. They're renting time on the Planet Finder optical telescope at Lick. And they have written memoranda of understanding with FAST, the large Chinese telescope that's just come online this past year. They've started working with the Meerkat array in South Africa, which is a precursor for the square kilometer array to be built probably in the 2030 timeframe. And they have a memorandum of agreement with Jodrell Bank in the UK and the array in the UK. So you can expect instrumentation to be put onto these telescopes and more observing to finish out their list of goals. So there's actually more SETI today on other telescopes, except not quite. They were working, we had SETI at home, was working at Arecibo and Alpha and Astropulse as well, until a cable broke this past month and damaged the telescope surface at Arecibo. So everything's off the air right now. They do plan to make a rapid repair of that dish structure. And so we assume that SETI at home and will begin operations again. All right, in the Netherlands and in the UK and across Europe, there is something called LOFAR, the low frequency array. And Sweden and the UK have begun to use 2 of those tiles to do SETI observing. There's a SETI group in Italy that uses a 64-meter dish at Medicina. There is a SETI group down in Apple Valley, California, which has moved, I think they moved the fence, not the telescope, but there is now a 26-meter former DSN telescope, Deep Space Network telescope, outside the fence at Goldstone. And they have started the Goldstone Apple Valley Research Telescope. And so students are using that telescope to do a sky survey. So a broad search that isn't very deep, but covers all the sky that can be seen from that location in Southern California. And there's another low frequency array in Western Australia called the Malura Widefield Array. And they are also beginning to do SETI observations. So now in the optical, students at Harvard built this wonderful optical SETI observatory that ran for years and years, and the last student has graduated, so it is not actually operating at the moment. It hasn't been for the last couple of years. But it looked at 80% of the sky that you can see from Harvard, Massachusetts, and night after night after night scanned the sky looking for bright optical flashes that lasted maybe only a nanosecond, because that's something that we can do with telescopes and lasers, but Mother Nature finds it very hard to do. So optical SETI is usually looking for time compression, bright flashes, although it also looks for frequency compression. So all of the data that are taken for radial velocity studies with the Keck Observatory in Hawaii, all of those data that are looking for exoplanets are reanalyzed looking for laser signals, that is frequency compression of laser light at only one frequency. There's an amateur optical SETI observatory called Boquete in, I'm blanking on Panama. That's the country. This is down in Panama. The near infrared project at Lick Observatory to push the optical SETI down to longer wavelengths in the near infrared. And then there's also archival SETI, which is looking at data that were collected for other reasons. In this case, the WISE spacecraft, which mapped the infrared sky, and those data have been reanalyzed, looking for what might be Kardashev 2 or Kardashev 3 type civilizations. Kardashev 2 is something like a Dyson sphere, which has the ability to manipulate the total power output of its star. And Kardashev 3, again, bigger on steroids, it can manipulate the total power output of its galaxy. So the WISE data have been searched looking for this kind of cosmic miracle. All right, there's, in the future, more optical SETI. So the Veritas array is an array of 4 telescopes in Arizona, and they have photodiode arrays at their focus with about 500 pixels. And they're looking for atmospheric trails. They're looking for Cherenkov radiation from high energy particles. But with some new software, not any new hardware, but just with new software, we can look and see whether occasionally just a single pixel, not a trail, but a single pixel lights up, and that it lights up from the same place on the sky, the same time at all 4 telescopes. So there's dedicated observing time that's doing this, and also archival searches through the Veritas data. Then in Southern California, Shelley Wright at UC San Diego, and also Paul Horowitz from Harvard, is using Fresnel lenses and talking about building kind of a geodesic dome structure. Here you can see the dome structure, and each of those elements has a Fresnel lens that can focus a large area of the sky onto modern detectors, photodetectors. And because they're interested in searching 10,000 square degrees of the sky, and are looking for transient events, you end up having to build not just one of these, but 2 of them separated by about 1 kilometer. And you use a coincidence detection at both telescopes from the same piece of sky to give you some confidence that the transient signal that you found is valid. There's also an optical SETI program being done at the SETI Institute. It's called Laser SETI, and it doesn't use telescopes or Fresnel lenses. It uses astronomical grade cameras, 8 cameras at each site, and a grating to spread out the spectrum. And it looks for bright point source flashes from a laser. And we think with about 15 sites around the world, we will be able to look at all the sky all the time. And the first of these sites has been implemented with a half observatory, that is with 4 cameras, at an observatory in Sonoma County, which we're hoping will weather the fires. And the second observatory will be on Haleakala when we can figure out how to deal with the quarantine and get the system down there. So this is, you can see the laser SETI up on the roof of the observatory. And in the future, there are telescopes that are being built for astronomical observations that we need to learn how to piggyback on, to do commensal observing as we have done with many radio telescopes and optical telescopes on Earth. This is now JWST, right, is the first one. And then what used to be W first is now the Roman telescope will be launching, and eventually something that's big, maybe as large as 16 meters. That's the kind of thing that you need to actually do the life detection, to actually go looking for these chemical fingerprints in the atmospheres of a significant number of nearby planets. We'd like to figure out how to use the data in a way that will allow us to find technologies. There's another telescope that looks really strange. All right, it's called the ExoLife Finder. It's being suggested to be built in Hawaii. Each of those mirrors is 6 meters across, and they're all phased up like a radio interferometer. And then as you watch an exoplanet go through its annual orbit around its star, and you stack together hundreds of orbits, you can then deconstruct the light curves to allow you to see something like an image of the surface where you can distinguish between oceans and continents, and you can look for biosignatures. Don't know what the decadal is going to say about ExoLife Finder, but it's a very intriguing telescope, and it really only will work for Proxima b, for that nearest star system. So it may be too niche an instrument for the astronomers to get behind, but I think it's just incredibly clever. All right, so what else are we doing? Well, the TMT, the GMT, the European Extremely Large Telescope, downgraded from the European Overwhelmingly Large Telescope. So this is the epoch of 40-meter telescopes. This is the next generation of 40-meter telescopes. And then the Large Synoptic Survey Telescope, which is now also named for Nancy Roman, will give us a snapshot of the sky every 3 days and show us things that are changing. Well, again, we want to learn how to look at these data for engineered signals rather than astrophysical ones. And we have PanoSETI and Laser SETI coming online. The new instrumentation that Breakthrough Listen will put on fast, and the Meerkat array, and eventually we hope the Square Kilometer array. The National Radio Astronomy Observatory is going to be proposing what they call the next generation VLA. It's being considered by the Decadal Survey those telescopes should begin to look a bit familiar to you, because one thing that the Allen Telescope Array has done is serve as a proof of concept for this offset Gregorian feed low telescope design. And so we have had an impact in future telescope designs, if not even in finding signals yet. And lastly, if you can make that life finder work, then here's something called Colossus. Again, a number of individual 6-meter telescopes, mirrors, phased up. This is big enough. This is 80 meters across. This, if it's ever built, would have the ability to find the heat islands, the heat sources from distant exoplanet cities. That would be pretty amazing. So I really enjoy talking to your astronomical association and to all of you, because I think that if I stretch your minds and make you think about SETI and what we're really talking about, it has the effect of holding up a mirror in front of each and every one of you and saying, see, all you earthlings, in that mirror, you're all the same when compared to something else out there. And it trivializes the differences that we find so difficult on this planet. And I think that that's a very good thing. I think that the more we can think of ourselves as earthlings, the closer we will get to finding solutions to the huge number of challenges that we face on the planet today: water security, food security, wars and disease, and challenges that don't respect national boundaries, challenges that will have to be solved globally. And so I like the idea of a mirror in which we all are the same. And I like also the words of Caleb Scharf, who's the chairman of the astrobiology department at Columbia. Caleb reminds us that on a finite world, a cosmic perspective isn't a luxury, it's a necessity. So my final words to you tonight are to give you a homework assignment. And that's when you get back to all of the devices which contain profiles about yourself. Change those profiles so that the first thing that you say about yourself is that you're an earthling. And then try and act like it. Thank you.
It was wonderful. Thank you so much. Let me see if in the chat channel on YouTube, I see any questions here.
Okay, I'm going to stop sharing my screen.
Oh, sure, that's fine. Well, while we wait for that, I have a question for you.
Okay.
So it was wonderful to hear about all these telescopes across the world, which are collecting data that you are looking for these techno signals in. What kind of data processing power? Like, I'm an engineer, so I'm coming from that side of the problem, where it must be terabytes, I don't know, zillion bytes of data, more than that.
Yeah,
And
it's
to just swift through all of that to find your answer is a unique challenge in itself.
Yes, and our ability to do that has gotten better and better as the computing has gotten faster. I mean, when we started doing this, we had to actually build our own chips to do Fourier transforms fast enough to get the work done.
Wow.
Now, in addition to industry driving computing to be faster and faster, the other opportunity that we have, of course, right now is to begin to use neural networks. So until now, we've told a computer to analyze data in frequency and time, looking for particular patterns, right?
Okay.
And maybe we've guessed the wrong patterns, right? So what we can do now with neural networks is to have the neural network tell us if there's any information content, not just a particular pattern. So we're being able to extend our searches looking for different kinds of things. And I find that a really exciting opportunity.
That's interesting.
But yeah, huge amounts of data.
Yeah, and that's where a little bit of SETI at home also started from, right? Where you wanted to harness the power of people's computers at home,
That's
and
right.
use that.
And so there's a tension between various parts of the community about whether to process the data in real time or near real time as a way of checking up on interference and human generated signals, because you can immediately reobserve, and that drives the need for speed. Or if it's better just to record huge volumes of data and then process it offline multiple times looking for different things. So we've always, at the SETI Institute, we've always been in the camp that says we want to do this data processing in near real time, because when we get a signal, and we do all the time, we want to be able to immediately follow up and figure out whether it's us or them.
Makes sense. Paul has a question. One possible answer to the Fermi paradox is that extraterrestrial is already here. Do you give that any weight at all?
I've seen no evidence for that, no credible evidence. People make claims. You wouldn't believe the equipment that people drag from their homes to the SETI Institute or to the Allen Telescope Array and say, see, this is, and I just, none of it is held up. Obviously, I want to answer that question. And so if there were data, if there were evidence that was credible, I'd be very eager to accept it, but nothing credible yet.
Got it. Rashi is asking, how can we contribute? Where can we contribute? What can we do from home with our telescopes or computers, or even help with coding or data analysis? Yeah,
I have a couple of projects that I could use some help on. And you should also contact the Breakthrough Listen folks in Berkeley. They're very good about using volunteer and student help. My challenge right now is that since I was a graduate student, I've been collecting papers on all of the searches that have been made. And 2 years ago, I put this into a large database called technosearch.seti.org. And it's built on Drupal 8. My coding ability with Drupal 8 is miserable. And so now that I don't have a student working with me on it, I could use some help. There have been more searches that have been submitted, and I need to update the database. So if anybody has skills in content management software and would like to help with this project, then just get in touch with me.
Well, there's your answer. Bring on your database expertise. So, wow, I got a few more here. Zai is asking, with the 9 dimensions, how many dimensional combinations have we tried so far?
Well, again, the best analogy I can give you is that glass of water out of the ocean or the hot tub. It's a part in 10 to the minus 23. If you want to know.
Wow. Okay, that's quite a lot. Let's see if Marianne has a question. Up until now, she really likes your term earthling.
Good.
But it definitely kind of fits as we step into the cosmos. So Kanch is asking, could you please talk about the Drake equation and how it is used these days in these searches? Are there competing calculations to the Drake equation? that drives the search for extraterrestrial?
Yeah, actually, the Drake equation is the agenda for a meeting. I'm sorry that it got labeled an equation because you really can't calculate anything with it. But here's how it goes, and that's because of huge uncertainties, right?
Right.
So Frank Drake was thinking about what you would need to know in order to estimate the number of potentially detectable technological civilizations in the galaxy. And he said, well, what you need to do is start with the rate of star formation in the galaxy. Then you need to estimate what fraction of those stars actually have planets. And those factors are ones that we have a pretty good handle on now. All right. How many on average, how many Earth-like planets would be in each planetary system? Of those planets, what fraction of them give rise to life? And of the life forms in the galaxy, what fraction of them develop intelligence? And finally, cultural evolution, what fraction of the intelligent species develop a technology and the ability to communicate? And then the very last factor, and the one that is so important, is how long. What's the longevity of that communication phase? So these are all multiplicative. People make lots of different assumptions about the different parameters. There are folks at Oxford who love Bayesian statistics, and they've gone bananas at this, and they've gone through the literature, and they claim that the most uncertain term is the F sub L, the fraction of planets on which life actually happens, abiogenesis. And they say that the guesses and numbers you can find in the literature are actually have 120 orders of magnitude of spread. Incredibly, incredibly poorly defined. So nevertheless, they do some wonderful statistics and have curves and all of this kind of thing. But that's where it's a beautiful way to organize our ignorance. I think that's the best way to describe it.
Okay, wonderful. I think I have one last question from Derek. Is gravitational wave modulation for communication by sufficiently advanced civilization, perhaps type 2 Kardashev or higher, considered remotely plausible?
It's plausible. There's certainly been some interesting science fiction that's written about it. We couldn't do it, right? We can't shake anything massive enough to generate gravitational waves, but they might. And so, yeah, people are actually even looking at that. I don't know. I haven't seen a published paper yet that says we've looked at these X number of gravitational wave events and analyzed it looking for this particular type of pattern or that particular type of pattern. But I will not be surprised when I see such a paper.
So it could be just around the corner, that discovery.
It might be.
Right. Yeah. I think that's the cool thing about this subject, right? Like you never know. You gotta keep looking till you find it.
Yeah.
So hopefully at some point we find intelligent neighbors somewhere around us in the universe. And we can confirm the theory that we are not alone.
Okay. Well, I think that's a great way to end. So thank you very much for having me.
No, thank you for having the talk coming to talk with us. And I wish we could be doing this in person, but unfortunately, the pandemic won't allow us that, and we have to be safe.
Yes.
So I'm glad we could make this happen, and thank you for your time. And on behalf of all of our members, thank you. Okay. Oh, there's one more question. Oh, there you go. Sorry, can I ask this one last question? Are we investing in launching more space telescopes by reducing their cost, or is the primary focus on ground-based telescopes for SETI?
Oh, well, people are trying to launch space telescopes. The Starshot project, which wants to build a huge laser facility and launch these fabulous sails that have all kinds of sensors on them. And the CubeSat that students are making that are sensors and telescopes. Yeah, the problem is it's a tragedy of the commons up there. It's we have so much stuff in orbit that collisions are going to become a really big problem. We've
Wow,
already
didn't think of it
seen
that
some.
way.
And so we have to adopt a new way of launching satellites and making sure that when they're finished with their useful lifetime, that we can deorbit them or boost them up into a very high, essentially garbage patch, get them out of the way so that we can continue to have access to low Earth orbit.
So space is already so crowded that that can become an issue.
Yes, space debris is a very large problem.
Okay, well, I guess we are done trashing the Earth, and now we are moving
Yeah,
outside the Earth.
Yeah, and
it's not a good trend.
We haven't yet actually come to terms with these planned huge 60,000 satellite arrays for data processing all around the world. What the sky is going to look like for both optical astronomers and radio astronomers is pretty disappointing.
Okay. Well, we will schedule another talk. We would love to hear more about that in the next one. But thank you so much once again for your time.
You're welcome. Bye-bye.
Thanks. Yeah. Bye. I'm just gonna